Modern enterprises are trapped in a physical contradiction. To function, their most critical data must be exposed to a global, decentralized workforce. To survive, that exact same data must be completely walled off from external threats. For decades, network architecture attempted to resolve this paradox through spatial boundaries. Organizations built digital castles, relying on firewalls to separate the dangerous outside from the safe inside. This created a model of spatial implicit trust. The architecture assumed that if a user or device was located inside the network perimeter, whether physically in an office or connected virtually, they were inherently safe. Because productivity mandates that remote employees have access, doors must be left open in these perimeter walls. Relying on spatial trust means that a single breached door compromises the entire castle. The shift to cloud computing and remote work completely dissolved that traditional physical perimeter. The organization's resources are no longer stored on premises, and employees are connecting from untrusted networks on personal devices. Now, a new variable accelerates this threat: AI agents. We are moving toward a topology where autonomous agents execute APIs, query databases, and perform tasks on behalf of human users at machine speed. The boundary of trust in enterprise networks is shrinking drastically. It moved from the physical network perimeter down to the endpoint device, and now it must shrink down to the individual data action. To understand why, we have to deconstruct the legacy castle and moat model, examine how zero-trust architecture restructures the control plane, and explore the new Beyond Zero framework required to handle machine-speed threats. Failing to update authorization architecture for these autonomous entities leaves an enterprise mathematically defenseless against modern credential hijacking. The legacy strategy for protecting internal assets relied on defense in depth, establishing multiple, nested zones of trust. This diagram illustrates the traditional perimeter-based architecture. Notice the distinct spatial zones: the public internet, the demilitarized zone, the trusted internal network, and the highly isolated privilege zone. To allow remote access, this architecture relies on a VPN gateway, but a VPN applies encryption only to the transit tunnel itself, ignoring the security health of the originating endpoint device. Once the user provides credentials, the tunnel is established. They receive an IP address in the remote network and instantly inherit implicit spatial trust. Look at the pathways leading from internal application services directly to the mainframe. A compromised payload on that remote machine now has an official backdoor. This enables lateral movement. An attacker can pivot from that single compromised remote node, explore the internal network, and access highly privileged systems. In a perimeter model, initial access equals total access. A single compromised endpoint effectively nullifies millions of dollars in firewall investments. Fixing this requires a radical design philosophy. Network locality must be rendered entirely irrelevant to access decisions. This reference model shows a zero-trust architecture, or ZTA. The rigid firewall zones and VPN choke points are gone, replaced by a borderless, identity-based perimeter. Notice the control plane at the top. This acts as the absolute authority holding the policy engine. Every single access request to any resource must be routed through and evaluated by this plane. Below it is the data plane. It cannot execute a data transmission, nor can it accept a connection from a requester without explicit configuration and permission from the control plane. This separation enforces a universal requirement. All entities, users, devices, and workloads must undergo continuous authentication and context evaluation, regardless of where they are physically located. Access is restricted strictly through the principle of least privilege. An entity is granted only the minimum access required to complete its specific mission, and nothing more. ZTA neutralizes lateral movement. Endpoints are no longer trusted insiders. They are untrusted entities, continuously proving their innocence to the control plane. Deploying zero trust requires architects to navigate a brutal trade-off between the granularity of access controls and the overhead of system integration. This chart maps that trade-off. Pushing policy enforcement closer to the specific resource yields higher contextual telemetry, but it requires heavy agent installation on every endpoint. The NIST device agent-based deployment model, utilized by systems like Google BeyondCorp, plots high on both telemetry and overhead. This schematic diagrams the device-agent model. There is tight integration between the agent installed on the enterprise system and the gateway attached directly to the data resource, providing real-time, highly accurate context. In contrast, this diagram illustrates the resource portal-based model. It relies on network segmentation and zero endpoint agents. The gateway sits apart from the unagented system, sacrificing deep contextual telemetry for ease of deployment. But regardless of the deployment model, all zero-trust architectures share a core limitation: the authenticated session. If an advanced persistent bread manages to establish a foothold on a fully authorized device, it can execute malicious actions within the bounds of that user's privileges without triggering ZTA alarms. Because ZTA authorizes access to a session or an application, it remains blind to malicious behavior executed inside that authorized session. The authenticated endpoint is the Achilles heel. Once autonomous AI agents act on an authenticated endpoint, the logic of monitoring human speed sessions no longer applies. To counter this, Google introduced Beyond Zero. This architecture shifts the boundary from application-level authorization down to resource-level authorization. This flowchart demonstrates the core mechanic. Every single action taken on a specific resource, like attempting to modify one row in a database, requires its own independent, real-time authorization. Expanding that dynamic check reveals a hierarchical reasoning engine. It pairs static, granular policies with a dynamic AI model that evaluates the actual intent of the action using enriched context. If the signals point to risk, this engine can autonomously deploy in-depth investigations or verification challenges at machine speed to contain a rogue agent instantly. To secure an enterprise against AI, the security infrastructure itself must operate as an autonomous, intent-evaluating agent. The history of enterprise cybersecurity architecture is a continuous engineering effort to systematically shrink the blast radius of a compromised entity. The perimeter model failed because location no longer equals trust. The baseline zero-trust model is reaching its limit because an authenticated session is no longer enough to guarantee benevolent behavior. Trust is no longer implicitly held. It is mathematically calculated, challenged, and granted at the exact millisecond of every single data interaction.